Thanks, Yannick, for the introduction. First I'd like to thank the organizers for giving me a chance to present this work in this nice conference. So it's a joint project I did together with Nina Zydiangian, who used to be a postdoc in my group in Warsaw, Mauro Morales from University of Sydney, and Zoltan Zimborash from Budapest. So I start with just introducing the concept of quantum computation advantage or supremacy. So, currently we are impressed by the developments in the field of quantum computing, quantum technologies more generally. Devices are having better and better fidelities. They are larger and larger, but still we are not yet at the level of fault tolerance. Couple of years ago, researchers proposed a paradigm that aims to come up with some tasks or problems for which those near-term restricted purpose quantum computers can offer speed up compared to classical computers. And typically such proposals, they come in the form of sampling problems. So you have some quantum circuit V, and your task is to sample from output distribution corresponding to this quantum circuit. What classical simulator is doing is actually it samples from a probability distribution that is supposed to approximate the target probability distribution in additive error. So this additive error is just a measure of closeness of probability distributions. And the general structure of quantum supremacy results is the following. So you start with the assumption that there exists a classical algorithm that approximates the target quantum probability distribution in this additive error to some accuracy epsilon. Then you use a lot of mathematics, complexity theory, like you need to prove a bunch of things. You also throw in some computational complexity conjectures, and you arrive at the conclusion that polynomial hierarchy collapses. So polynomial hierarchy is this like onion of complexity classes that generalizes the famous P versus NP problem. So if you and people in theoretical computer science believe that this hierarchy does not collapse. So if you have some quantum process for which you can you can prove about a bunch of things, and I'll be discussing that later, you can convince yourself that most likely there exists no classical algorithm that would be simulating this process. So, and your confidence is then built in theoretical computer science, not in, say, your belief that certain problem, that certain classical simulation techniques are expensive, like exact diagonalization, for example. And there are two main platforms so far for attaining quantum supremacy: random circuit sampling, in which you have some array of qubits to which you apply at random layers of random circuits, and you measure in the end. Or you have boson sampling that many of you have heard, I guess, before. So you have some photons that input this interferometer. They scatter in this inner optical network, and then you measure particle number statistics in the output. And those two proposals, they enjoyed some nice experimental demonstrations in recent years. So random circuit sampling was demonstrated by Google about 2 years ago. Just this year, there was some follow-up work by people from Hefei, I believe, with slightly larger size of the system. Also, Gaussian version of boson sampling has been implemented experimentally last year in system of up to 50, 70 photons in 100 optical modes. Still, those those schemes, they have their issues. So you have a problem with their certification. You need to worry about the possibility of spoofing by efficient classical simulators, and they have different guarantees for hardness. And okay, so this is like simplified state of the art. Like this is what we do in this project. So we introduce like a fermionic analog of boson sampling. So we have a system of a bunch of fermionic modes, and we initialize the system by like a tensor product of such states. Okay, so that are like JZ type of states written in mode basis. Right, then we apply passive or active fermionic linear optical transformation. I will be describing what I mean by this in a second. Then we measure the output distribution. Right. And we claim that this is a very good candidate for, like when you take random FLO circuit here, we claim that this is a good candidate for quantum supremacy. And our main results are as follows. So we prove solution of output probabilities. We prove that it's on average very hard to compute them, like output probabilities exactly and approximately. And lastly, we give efficient method for certification of unknown fermionic linear optical transformation. So what I mean by fermionic linear optics, so I just introduce some notation. So I'm dealing here with fermionic system with D modes. The corresponding Hilbert space is fermionic Fock space. That is a direct sum of like spaces with definite fermion number. I have action of creation annihilation operators in this space. I can form their Hermitian counterparts, that is Majorana fermion operators. My whole space is spanned by Fock states. And now, like having introduced this notation, I can introduce passive fermionic linear optics. So this is a class of transformations in my Hilbert space that amount to just linear transformation of annihilation or creation operators according to like unitary taken from unitary group on dimension D, when D is the number of modes. In the language of first quantization, this amounts to just applying the same, it's like non-interacting evolution. So every particle is evolved according to the same unitary. Okay, it's a representation of a unitary group. Active FLO is, on the other end, like class of, it's you can know it under the name of Bogoliubov transformations. So those are transformations for me that are like, you can describe them by just orthogonal transformations of Majorana modes. And this is again a representation of low dimensional Lie group in our space, like in this case SO to D. Now, sadly, as far as I'm aware, it's not easy in the lab to implement such transformations for fermions. So for photons, it's actually very easy because you have those interferometers, like passive bosonic transformation is easy. But for fermions, it's in general, as far as I know, more difficult. So what we propose is to just apply Jordan-Wigner transformation and to simulate this process in qubits. So, Jordan-Wigner is a mapping from fermions to qubits. Fock states are mapped into computational basis states. Majorana operators are mapped into strings of Pauli operators, suitable strings of Pauli operators. Particle number measurements are mapped to computational basis measurements. And moreover, local particle preserving quadratic Hamiltonians are mapped to some local Hamiltonians in the one-dimensional qubit architecture. So using this, we can, like this dictionary, we can actually compile FLO transformations in qubits. right? So we use those decompositions of those low dimensional Lie groups known from optics. So Reg decomposition or Clemens decomposition, you might know them, right? But now, like after this Jordan-Wigand transformation, those nearest neighbor mode rotations, they are mapped to just nearest neighbor qubit transformations. So this gives us a result, like it's a known fact that you can implement arbitrary FLO circuit in linear depth in one-dimensional qubit architecture. And it's nice that actually gates that are required in those interferometers here, they are native to superconducting qubits, and they were already, like, those layouts, they were already used in the context of quantum chemistry. For example, in a recent paper by Google that did some like VQE type of schemes with like for Hartree-Fock. Okay. Now, so this is like motivation. That was just motivation why what we propose is experimentally feasible. Now, let me move to our first results, namely efficient tomography of FLO circuits. So if you have a general many-qubit quantum channel, it's very expensive to characterize it. It's exponentially hard. But if you assume that it's from this class FLO, it turns out to be quite efficient, quite easy. So the scheme is as follows. So we prepare a certain very specific, easy to prepare single qubit state, a bunch of them. And then we measure Pauli strings in the output that corresponds to Majorana fermion operators. And we collect statistics for different input states, for different measurement setting in the output. So this allows you actually to reconstruct this orthogonal transformation that is underlying FLO circuit here. Okay, so it encodes it encodes the circuit sort of uniquely, and just tying this all together and doing some math, some random matrix theory, you can get the result that you just by repeating this experiment many times, you get estimate to your circuit, okay, to accuracy epsilon, the diamond norm, using just number of measurement rounds that scales like the number of qubits or number of modes to the power 3. Okay, which is a very nice, because it's not exponential. That would be the result for the general circuit. Okay, so that is the first result. Let me now move to hardness of sampling. So some of you might know that actually free fermions, they are easy to classically simulate on a classical computer, and this is the reason why before our work there was no Fermion sampling type of proposal. Okay, so when you have input fermionic state that is free in this setting, so it's like fermionic Gaussian or it's a stated determinant, then the corresponding sampling problem is easy for classical computers. And this is you can understand this as manifestation of a dichotomy between fermions and bosons, because scattering amplitudes for bosons are given in terms of permanence, while scattering amplitudes for fermions, they are given in terms of determinants. And the former, determinants are much easier to compute than permanents that in general require exponential time. Okay, so that is the reason why you need those magic states in the input. So there are like superpositions of Fock states. You see on every 4 modes you have such a superposition, and like it was proven some time ago by Dmitry Ivanov that scattering amplitudes in this process, they are given in terms of mixed discriminants that are actually superpositions of determinants, or sums of determinants. So and it's hard actually to compute those in general. Right, but this is not the end of the story, because actually hardness of computation of specific probability amplitudes for specific circuit is in general not the same as hardness of sampling or approximate sampling. And people know this in our field for a long time. And okay, I don't have time to explain the details. There are just to say quickly, like you have some more or less standard but a bit lengthy reasoning in complexity theory that tells you that you need two properties to infer this hardness of sampling. You need anti-concentration and you need average case hardness of approximating output probabilities in relative error. So this latter thing is not proven for any proposal so far, so we can only support it by having like average case hardness of approximating output probability up to some small additive error. And okay, this is what those are our main technical results. We prove anti-concentration for FLO circuits, and we prove average case hardness of approximation of those circuits. Okay, so it will be just shouting out with some mathematics. So yeah, we prove this anti-concentration.
Slowly.
I should be
slowly finishing.
I have like 4. Yeah, sure. I know.
But there's time for questions, so please.
Yeah. So this first result tells you that with high probability, with significant probability over the unitaries taken from the circuit, from this ensemble, your output probabilities are not too small. Okay, and we use some techniques based on representation theory to prove it. And importantly, you cannot prove with using standard techniques that are based on designs. So this is one thing. Another thing is that, okay, we use this nice technique based on K-only path deformation to prove average case hardness. And what? Like, okay, so we prove that it's should be hard to compute exactly output probabilities with probability greater than 3/4 for random choice of circuits from both active and passive FLO. And we prove average case hardness for computation of output probabilities to some small accuracy. Just this year, there was some like improvement by Bullant and others, and you can actually get better error bound than what we initially claimed. Like from n cubed, it's like to the n squared. Okay, so this is more or less my last slide. So a comparison with other quantum advantage schemes. So okay, so random quantum circuits, they have anti-concentration, they have worst case hardness for output probabilities, they have average case hardness. It's not easy to certify them. They were experimentally realized. Boson sampling, on the other end, anti-concentration has not been proven. There were like other things are present there. Okay, maybe standard boson sampling is not that easy for experiments. Okay, in this work, in one go, we sort of proved anti-concentration, this hardness, and certification. Okay. We hope maybe at some point we'll be able to do experiments. Let's see. So to conclude, we propose a fermionic analog of boson sampling. We claim it's experimentally feasible in, let's say, using architectures of superconducting qubits. We gave strong guarantees for hardness, and we showed that it's possible to certify unknown FLO unitaries efficiently. With regards to open problems, so I would really want to have some genuinely fermionic realization of the scheme without resorting to qubits. Also, we are actively working about extending our verification and certification results. And we have some promising results about this. Thank you for your attention. Yeah.
Thank you, Michał. So unfortunately, you went over time, so I cannot allow for questions, but Maciek asked a question and you answered it because he was asking about... Yes, so maybe there is something from the floor. The organizers are allowing to extend the session. Anything from the... Yes, and Rafa.
Okay, so I am allowing myself to ask the question. So Michał, but isn't it so that if you translate everything to qubits, in the end, this fermionic sampling amounts to some specific random circuit sampling with some particular measure? So what would be this measure?
That is no. You're right, Rafał. The difference, I totally agree with you about this. So then the difference is under this translation. If you don't implement it using fermions, our scheme you have better certification properties compared to standard random circuit sampling, and like mathematically it differs a bit, but yeah.
Okay, thank you, Michał. So let's us thank Michał once more.
Thank you.